Welcome to mini lesson 20. Today we're going to complete our calculation of the multiplicity of the ideal gas using phase space geometry tools. This is still from Schroeder section 2.5. So what we've done so far is we have constructed an abstract phase space out of all the coordinates and all the momenta of the atoms in the gas. And we've argued that we can break the multiplicity of the ideal gas into two independent factors, one corresponding to the coordinate part of the phase space and the other corresponding to the momentum part of the phase space. And so, for example, the constraints on spatial coordinates of atoms in the gas are that every atom has to be within the given volume of gas V, and so the phase space constraint that they're all in this volume V gives you a coordinate space multiplicity of V to the nth power. So one factor of V for every atom in the gas. The momentum constraint is more complicated. Each particle has to have three components of momentum, and they have to combine in such a way as to be consistent with the total internal energy of the gas. And so the constraint is that the sum of all squared momenta magnitudes over all the atoms in the gas has to be 2 times the mass of the atoms times the total internal energy U. And so this sum of squares being equal to a constant defines the surface of a sphere in the momentum part of the phase space, and the radius of the sphere is just the square root of this constant. So the possible coordinate values of all the atoms have to lie within a volume V. The possible momentum components have to lie on the surface of this special sphere defined by the energy constraint. So this is a hypersphere because there are many, many atoms in the gas, therefore many, many momentum coordinate axes. I've only drawn 3 here. But the dimension of the hypersphere, or the dimension of the space in which the hypersphere is embedded, is 3n. So 3 momentum components, n atoms. And then we need to be on the surface of that hypersphere to be consistent with this energy condition. So how do we count states on the surface of a hypersphere? The answer is we have to calculate the surface area of the hypersphere. And so last time we identified that we could write the general volume of a d-dimensional hypersphere as some constant times the radius of the sphere raised to the power of the dimension. And then the surface area would just be the derivative of that function with respect to the radius. So d c sub d r to the d minus 1. And this surface area measures the available momentum states consistent with the given energy. So in other words, the multiplicity of this momentum part is the surface area of the 3n dimensional hypersphere with a radius equal to the square root of 2mu. Right. So surface area measurement in high dimensional space is our analogy of counting in a discrete set. So the only thing we have to do in these slides, really, is calculate the value of c sub d. Right? That coefficient is the only thing that we don't know in this problem right now. Right? We know the radius in terms of the energy. We know the dimension in terms of the number of particles. We just don't know the value of c sub d. So let's get it. And so if we look at the surface area S sub d, and recall that we got it by taking a derivative, we can rewrite the derivative as the differential volume element associated with the hypersphere is this expression for S sub d times dr, right? So that's the thing we would integrate if we wanted to know the volume of the hypersphere. We don't really want to know the volume of the hypersphere in this calculation, but we're going to sort of use it formally. And we should keep in mind that we could also imagine doing this whole thing in Cartesian coordinates and saying the differential volume element is just equal to the extended product over all the dimensions of the space times each individual differential element. And so you'll see products like this underneath integral signs in a lot of what we're doing, and that's important for what we're about to do next. Right, so this would sort of be the standard Cartesian product, whereas up here we're basically working in a sort of modified spherical coordinates where we aren't thinking about the angular variables because the sphere doesn't have any angular dependence. So let's imagine picking an integral that we know something about, right? That would somehow involve this extended product and therefore would involve dv, right? And if we knew enough about the integral, we could imagine using it to extract c sub d from the dv expression. That's basically our strategy in this calculation. And one of the integrals that we know from our last lesson is the Gaussian integral, right? That e to the minus x squared dx integrated over all the real line is the square root of pi. So what we can do is another special trick with this. What if we made a product of d copies of this integral, one for each momentum coordinate axis, or okay, in this case we're sort of thinking about arbitrary dimension d, but one for each coordinate axis, okay? It's kind of the same as how we made two copies to deal with the Cartesian plane in order to get this answer in the first place. Only now we're going to do it for d copies. And so instead of having an e to the minus x squared plus y squared, we've got an e to the minus sum over all the dimensions x sub I squared. And then we've got this extended product here, which is just the same as this dv. But whatever the case, when you make a product of d copies of this integral, you just get the square root of pi raised to the d power. So that's going to be pi to the d over 2 is equal to this integral. And so the important point is that the integral automatically contains dv in this spherical form, okay? And so let's just go ahead and substitute that in and see what it does to the integral. So in other words, we're going to convert from Cartesian coordinates to something like spherical coordinates, where capital R is now the square root of the sum of all coordinates squared that you would see here. So this would be r squared. So the basic idea is that this thing in the exponential just becomes r squared. This product of differentials becomes just the differential element of the surface area. So that's this whole expression times dr. And one thing to note is that we've sort of gotten rid of this multiple integral sequence, right? Because now instead of doing an integral over each variable in turn, we've incorporated all the x sub I variables into the variable r, and we're just integrating over r, right? And this is essentially exploiting the spherical symmetry to say that, look, whatever the angular part of the integral here is, it doesn't depend on r, it's uninteresting, and so essentially any angular factors would come into this c sub d. All right? And so if you want a more formal manipulation, I sort of did something here to show you how this integral over this product sort of reduces to an integral over the radii. But what are we going to do now? Well, we've got an integral. It contains c sub d. We can factor d times c sub d out of the integral. And then the nice thing is the thing that's in here is a known integral. Okay? And so one possibility if you've got a known definite integral is to sort of just stop and say, look, that's a number. I'll plug it into my computer and I'll tell you what the number is, or I'll look it up in a table or something. That's not possible in this case. There's nothing wrong with that strategy if you can get away with it, but we can't get away with it here. And the reason is This is a known integral, but it depends on the value of d. And in our calculation that we're doing, d is a physics parameter, right? D is 3n, where n is the number of atoms. And so this is not something that we can just sort of sweep into a number we can pull from a table. It actually would change depending on the physical system, right? And so we have to work carefully with this integral to figure out the dependence on this physics parameter. And so in order to do that, I'll call that special integral that I claim is known capital A of d, right, to indicate that it is a function of d. And then I just want to change variables to try to put this integral into a form that's more obvious. So let's let x equal r squared, and then dx is 2r dr. We can solve for dr as dx over 2 square root of x. Substitute all these things back up in here to get an integral in terms of x. And you get that a of d is equal to 1/2 the integral from 0 to infinity of e to the minus x, x to the d over 2 minus 1 times dx. It doesn't really look like I've done anything useful, but this integral, it turns out, is exactly the form of the expression for factorial from Schrodinger's appendix B3, right? So I'm writing it in a little bit different way than Schrödinger does to make the connection with this more clear. N minus 1 factorial integral representation is integral from 0 to infinity, e to the minus x, we've got that, x to the n minus 1 dx, right? And so here we've got exactly n minus 1 if we identify n equal to d over 2. And so the result is that this integral that I say is known is exactly 1/2 d over 2 minus 1 quantity factorial, where now d is this physics parameter that's 3 times the number of atoms in the gas. So from here, we can go back to our integral and say that pi to the d over 2, which came from just concatenating a product of Gaussian integrals, is equal to d times cd times this integral, which we now know is just a of d. So 1/2 d over 2 minus 1 quantity factorial, right? And so I'll erase the integral from there and set the pi to the d over 2 equal to this expression. And all we have to do now is solve for cd, which is what we wanted in the first place. So here we go. Solve for cd. It's 2 pi to the d over 2 divided by d times d over 2 minus 1 quantity factorial. Let's go ahead and sub this cd now into the expression for the surface area of the sphere. So one nice thing is that the d in the denominator cancels with the d here. And we're left with this expression. So we're going to now keep taking steps towards physics. This is just generically the surface area of a d-dimensional hypersphere, right? And so to put physics into it, we remember that capital R is the square root of 2mu, and the dimension is 3 times n. So you can substitute that in, and this is exactly the number of available momentum states consistent with the macroscopic energy constraint, right? So the number of states that live on this surface that are allowed to be involved in microstates of our monatomic ideal gas. So it's a pretty cool trick, I think. We basically, as I said a few lessons ago, just sort of turn the Gaussian integral calculation on its head, where instead of using geometry to calculate an integral, we now use the integral to calculate something about geometry, namely the value of this c sub d. But we got a little ways to go yet, because we need to try to put all this together. So we need to take our omega p, the number of allowed momentum states on the hypersphere surface, multiply through by the number of allowed microstates associated with the coordinate space. So that's just v to the n. So we get this extra factor of v to the n. So there are two issues we have to deal with this formula. This formula is not usable as it stands. The first, and they're serious issues. They're not just that there's big numbers and factorials. We'll deal with that later. But they're two really serious issues. Number one, we got a bunch of small numbers. Okay, actually, that's not a serious issue. I shouldn't have said that. That's a trivial issue. But the really big issue is that the multiplicity is not dimensionless, right? We've got a volume to the nth power, which is cubic meters to the nth power. And then we've got a momentum to the 3n power, which again is a momentum unit to the 3n power. So that's not dimensionless. And yet multiplicity is supposed to be a count, right? How many microstates are consistent with a given macrostate. And so we need multiplicity to be dimensionless. We've got to fix that. Let's start with the first thing, the small numbers. So the first thing we can obviously do is note that in this exponent 3n minus 1 can just be approximated as 3n because for large n you can drop the 1. And the same thing down here in the factorial, 3n minus 2 for large n is just approximately 3n over 2. Okay? So drop the 1s is all I'm saying. Then in addition, I want to drop this 2. This is not super essential to do, but just for the sake of simplicity and consistency with your textbook, we can drop this. All right, so basically saying 2 is approximately 1, and the reason that's a legal operation here is because everything else in this formula is either an exponential of a huge number or a factorial of a huge number, right? And so multiplying by a number that's just of order 1 or 10 or even 100 is an irrelevant operation. So you can just drop it. If you don't like that, I can point you to places later in our calculation where you'll see how it would have been dropped anyway. So we drop it now. And so the expression we get by dropping all that is pi to 3n over 2, blah, blah, blah. Drop everything. But it's still not right. So this is not the final expression. Well, so now let's deal with the dimensions. So if we've got SI units on these quantities, right, our omega v factor would be meters to the 3n power. Right, we integrated over 3n position coordinates to get that volume for each atom. And then omega p is momentum units, kilograms times meters per second to the 3n power. So somehow we need to multiply by a constant that cancels out these units. Okay? And so you might just say, well, let's just call it a constant and we'll figure out what it is by doing experiments. That would be possible to do, and I think, you know, that was the procedure that had to be taken in the early days of statistical mechanics. But now we know about quantum mechanics. And there's one thing you should keep in mind is that our phase space is made up of positions and momenta. And we know from quantum mechanics that you can't measure positions and momenta to arbitrary precision, right? So the Heisenberg uncertainty principle says the uncertainty in the position of a particle times the uncertainty in its momentum in that coordinate direction has to be bigger than or equal to h over 4 pi. And so this is also a product of momentum and position, right? The units of h are joules times seconds in SI. And so if we raised h to the 3n power, we would have a quantity with the same dimensions as this version of omega. And in particular, there's a physical interpretation to thinking about this, which is that h sort of represents the smallest phase space, or let's say h cubed, I should say. H cubed is the smallest phase space volume for a given atom. And so, you know, for all the n atoms, the smallest volume that makes sense is h to the 3n, where volume is sort of reckoned in the same units as this. Okay? And so because of our knowledge of quantum mechanics, we're actually able to rationalize the meaning of the constant that removes the dimensions from this expression. again, there could be you could drag along the 4 pi with you, but ultimately we would end up erasing that 4 pi because that's a number of order 1 that would be negligible compared to all the other exponential numbers in the multiplicity. So what we're going to say now is that we need to divide omega v times omega p by h to the 3n to make it dimensionless. That's one thing it does. But the other thing it does is it acknowledges some aspects of the quantum nature of matter by incorporating uncertainty principle lower limits into the geometry of phase space, right? It says if you try to break phase space up into smaller chunks than the uncertainty principle, that's not allowed. All right, so one more issue to deal with that's not super obvious, but that people figured out pretty quickly even before they knew about quantum. And that is that the calculation we just did in phase space overcounts the number of available states in omega v and omega p, because within omega v you only consider the volume, and that allows you to count as distinct configurations where you would take this atom and swap it with this one, right? And in particular, it counts all the permutations of all n atoms as distinct, and that's not allowed, right? It's not physically reasonable that swapping two like atoms would give rise to a different configuration. And so we need to divide out the number of permutations of n atoms taken n at a time, which is n factorial, right? So this is an order matters issue because we're talking about the specific spatial arrangements of the atoms inside this box needing to be divided out. All right, so now we've taken care of everything. We have omega dimensionless. We have permutations of atoms now divided out and not counted as distinct configurations. And so in final form, the multiplicity of the ideal monatomic gas looks like this. We've got the same thing that we had before after dropping small factors, but now we have an n factorial and an h to the 3n in the denominator. And this is our big result. So put it in a big box. Are you going to have to derive this on an exam? I mean, it's open note, right? So if I asked you to derive this on an exam, you would just copy. So the short answer is no. The long answer is you will have homework problems related to this, using this and trying to understand how this form would arise in different contexts. And so let me just give you an example. If you look at this and point to the important pieces, you see there's a 3n that appears that comes from the dimension of the momentum part of the phase space, right? There's 3 momentum components for every atom. So every time you see a 3n, that's where it came from. Another important physics fact is that the total space occupied by the gas is here given by V, right? And so that's something that could potentially change. Say, for example, if you go back a few lessons to when we were thinking about gas atoms confined to move on a line, right? And so if you were confined to move on a line, you wouldn't have a factor V here anymore. You would instead have a factor of L, right? And in particular, then the power of h that's required to non-dimensionalize this would be slightly changed. Right? You would no longer have a 3 to the n. If you were on a line, you would now have what? What would it be? It's an interesting question. Some other number that actually correctly counts the total dimension of the x times p x along the line. So, physics implications of this formula. More volume gives you a higher macrostate probability. That's fairly obvious, but it's also extremely strong effect, right? It's v raised to the nth power. Very significant. More internal energy, same deal. Right? Higher macrostate probability, and it's exponential. More particles, Yes. It's appearing as an exponent. Well, the factorial's in the denominator, so that's complicated, right? So but it's pretty intuitive what this means. What we're going to do next time is take this expression and use it to calculate an explicit function of U, V, and N for the entropy of the monatomic ideal gas using the Boltzmann formula. And what we'll see is then that becomes really intuitive, and I think you get a lot of physical insights from that. This expression I find difficult to really say useful things about, but the entropy turns out to be really useful physically. All right, so we'll see you next time.